All right, hello everyone, welcome. Good to see you guys. I hope you all had a great week last week. Got a chance to look at the problem set and digest some of the material that we went through. Gabe will be having our first problem solving session today after this class for 1 hour from 11 to 12 Eastern. And he will be going through the problems and also giving you some more mathematical intuition and giving you a better idea of the kinds of mathematical tools that we're going to need. Unfortunately, I don't have time to develop all of them in depth here, and so that's sort of the purpose of the problem-solving session. Does anyone have any? I hear some feedback, maybe. If you don't mind all muting yourself, unless you're going to say something. Does anyone have any quick questions before we get into today's material? You can put it in the chat, or you can just call out. And we'll start in a few minutes. Just give some time for people to trickle in. Did everyone find the YouTube channel okay? Yes? Okay, good. Yeah, that was a good idea that my brother had. He's like, just put these on YouTube. So hopefully that makes things more accessible for everyone in case you can't make it to one of the live lectures. So this problem solving session is going to cover today's material. Yeah, so it's going to be last week's material and the first problem set. And the second problem set will be up tonight. So the first problem set was more of a computational exercise. If you looked at it, it wasn't really in depth. The second problem set that I wrote out is much more indicative of the kinds of problems I'm going to have you solve. And you'll see that you're going to start figuring things out on the way, and it's sort of going to lead into the next lecture. But the problem solving sessions will always be covering the material from the week before. Okay, let's get started. So before I start with some new material, I want to go over one of the concepts we learned last week. And the reason I want to do that is because I think I went through this too quickly, and I didn't highlight the importance of this object that we constructed, namely the expectation value. So the expectation value is a really important object, okay? And I want to stress that. It's a really important object because it is the actual mathematical object that yields us some observable value, right? We use this construction of the expectation value to yield us some number of a physical property, right? And at the end of the day, what we want to do is measure physical properties. That's what any physical theory wants to do. And so I sort of just threw it on the board and I said, this is an expectation value. And I didn't really guide you through it, and I didn't really explain to you the rationale behind such a construction. So let's start with that today. Let's start with the expectation value. And you'll recall from last class that I have the following construction for my expectation value. Okay, and I've constructed this in a very particular way. This isn't just sort of some random thing I've constructed, right? It's supposed to yield a number corresponding to a physical observable. And that's really important to keep in mind. So let's work this out. Again, you should recall that these bras and kets are nothing else other than state vectors. They're state vectors in a complex vector space, in a complex plane. This is not a state vector. This is some scalar. This is some number that we want to pull out, right? And so this is going to tell us some hard physical value. Whereas these two things, which are state vectors, are not necessarily going to give us a hard physical value. They might tell us about the dynamics of the system. They might tell us what vectors are operating in the vector space. But this is really what we're after. We're after some value, some quantum number that we want to compute. So let's see how this manifests itself. So let's compute the expectation value with respect to some measurement, A prime. And again, before we do that, I want to stress one other thing really quick. There's a difference between this capital A and this A prime in our notation. There's a big difference. This capital A is the physical characteristic we want to measure. So this capital A is like momentum or velocity or whatever physical dynamical variable you wish to measure. This A prime is the actual number measurement or the actual state of that physical quantity. So let's say I want to measure momentum. Great. So A represents momentum. Well, then A prime will tell me the state of my vectors corresponding to momentum, right? So it tells me more about the dynamics of this physical quantity. So this is just sort of a label, and this is telling you how you're going to get to measure that physical quantity. And it's important to make that distinction, right? Because here I have this capital B, which is in my expectation value, but I'm using little b's, okay, in my construction. So that's important. That's subtle, but it's important in the notation. And it's gonna matter a lot more when we get to the Pauli algebra in a minute. Anyways, so let's compute this. Right, and you get this following object, which is what we wrote down last time. And now you notice something. We have two scalar products. Another phrase for this kind of object is an inner product. So we have two inner products, and sandwiched in between we have some scalar. So of course we get our kronecker deltas. Right? And so the only way this works is if these two kronecker deltas equal 1, that means A prime is equal to B prime, and if you multiply a scalar by 1, you get back the scalar. And so you see we've sort of constructed this in such a way to get back some scalar, okay, if it's operating on some other measurement A prime. Also, again, I just want to stress, if you have questions, just put them in the chat. Don't feel like you're interrupting the flow of the lecture. It's good if we have some back and forth. That's important. Why does the summation vanish when you introduce the kronecker delta? Why does it work only if it is equal to 1? Okay, so the summation is just a formality. Thank you for bringing that up. It's really just there just to emphasize that we're summing, we can sum over all possible B primes, right? I can add a B double prime, a B triple prime, a B quadruple. That's just what it's trying to emphasize. So, you know, I just took it out kind of carelessly, but it's not really there for anything, for any formal reason other than to remind you that we can sum over all possible B primes. Does that make sense? And if you ask a question and I follow up, just, you know, feel free to talk, just so I know, and I don't have to keep looking at my screen. Does that make sense, Kelly?
Yeah, it makes sense.
Okay, good. Okay, Olha, why does it work only if it is equal to 1? Okay, good. So remember, these kronecker deltas equal 0 if A prime does not equal B prime, right? And so this term would just vanish if A prime does not equal B prime. If A prime does equal B prime, you get a 1 as these kronecker deltas. So you're just multiplying the scalar by 1, right? And you get back the scalar. Does that make sense? Yes? Okay, good. And are prime values scalars? Well, yes and no, right? If a prime value is in this, it's not. It's a state vector. If a prime value is outside the bra or ket, then it's a scalar, right? If you take the inner product of two state vectors, you get a scalar. So yes and no, it's really, it depends, right? It's like saying, oh, I have some function of momentum, right? Okay, that's not a scalar. It still has to do with momentum. It's still describing the state of momentum, right? But that's not a scalar. The scalar would be that, you know, momentum equals 5 or whatever. And that might come from the function of momentum when you do some mathematics to it. So no, that's not a hard and fast rule. Really, this bracket notation is meant to describe to you what's a state vector, what's a scalar, what kinds of combinations yield what. Does that make sense, Vu? Yes, okay, great. Okay, so let's just play around with this a little bit. Let's just do some quick computations. So if I have this combination, I'll get this object. Right? So, you know, this is totally arbitrary. We're just doing some practice with. In the first line, there's a bra B prime and a ket B prime. Why did they both turn into kets in the second line? Good. So remember, which line are you talking about?
Oh, sorry, it was the previous board, like before you erased it.
Oh, okay. Was your question cleared up or?
No, so it originally it was like ket B prime and then scalar B prime and then.
Oh, yes, very good, good. So that's notational, right? So when I have my expectation value, sub A prime, right? It just means that I'm adding in a complete set of, like another inner product of A prime. And
Right.
in between that inner product, I'm sandwiching in my expectation value, right?
Yeah, but I don't understand.
Does that make sense?
Yeah, but I don't understand why it would be like it turned into like, do I read it like bracket A prime bar, or I don't know how to read it, but.
Okay, can we go over it during the break?
Okay, yeah, sure.
Okay, yeah. Sorry, I skipped it. Yeah, that's why it's tough in the chat, guys. So I much prefer you just talk and just, you know, holler like, hey, what'd you do there? Because I'm not looking at the chat in real time. It's a little far away from me. Okay, so just make it a habit just to speak the question. This way I can answer right away. Okay, so let's just do the opposite calculation. Just to give you some practice, it's a little trivial, but again, when you're first learning something. For the same reasons, you just get the opposite result. Okay, so I just wanted to review the expectation value before we get to the Pauli algebra, just because it's so important, and we're going to be using this concept so much that I wanted to make sure you really just got the mechanics of it. Okay, any last questions about this before we go to the Pauli algebra, what the physical significance is, or anything at all?
So the last time you wrote the answer, you had a summation before it. Do you still need it here?
You could, again, you could keep it there if you want to imply, you know, just to keep it in your mind that you're summing over all B primes, right? I could just have, for example, if I dropped it and, you know, I was summing over all B primes, all I'm saying is I could have some B double prime, some, you know, dot, 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 all the way up to Bn. right? That's all I'm saying with the summation. I think this sign is just very, very like intimidating for people. Like everyone is always just like, wow, what is the summation doing? It's really, really just a simple little thing. I don't know why we make it such a big, daunting sign. It really doesn't have to be. So does that make sense?
Yeah.
Okay. Yeah, it's just kind of there. I mean, we're doing things extremely abstractly right now. And so you shouldn't put much stock into what I'm actually writing down, only to emphasize certain aspects of what we've learned and just reinforce them. I could have easily left the summation out. I mean, and now that doesn't mean that this is equal to the identity operator, right? Right? Don't get confused, because the identity operator looks very similar to this. Or the projection operator, that's another name for it, because it projects and you get the same state vector back. That's not what this is, right? Because you have this scalar sandwich in between. Any other questions before we go to the Pauli algebra and to the new stuff? Could you leave this on the board just another 30 seconds? Sure. Again, I really, really am encouraging you to speak because I'm not going to be looking at the chat much longer now. It sort of gets in the way of the flow of what we're doing. So please just speak up when you have a question or you have something that's important. It's already impersonal on Zoom, and so I don't want to relegate our discussions over chats. Okay, can we move on? Is everyone good? Okay. He said he's good. Okay, so let's move to our first sort of physical description of this. And you're going to see that some of this weirdness mathematically we've been discussing is really going to explicitly manifest itself. And you might be a little shocked when it does manifest itself the way it's about to, but at the same time, remember that we've already discussed some of the craziness that's going to pop up. For example, we're going to see explicitly why we need imaginary numbers in a probabilistic theory of dynamics and a probabilistic theory to characterize physical laws. That would sound insane, but we know that that's not so out of the ballpark of what we're trying to describe. So now, the analog to our capital A is this sigma z, right? So now we're going to develop the Pauli algebra. And what this represents is the spin along, the measurement of spin along the z direction. Okay, so now I'm actually explicitly telling you what my physical quantity of interest is. And of course, now the analog to our A prime is sigma z prime, which would equal +1 or -1, right? Depending on whether it's spin up or spin down as we're measuring along the z direction, right? You won't get any spin 1/2 because you're not measuring along the 90-degree angle, as you've seen in your problem set. Okay, and let's just work out some identities. So sigma z, or sorry, if I have this combination, I get this identity. You can work out the algebra. That's a z. My z's in 2s, and that's a 2. That's a 1/2. Okay, I'll put a line through my z's to make it clear. Just so you don't get so. And this is also the direct analog of what we did with our probabilities, right? It's just playing around with the measurements and the geometries and all of that, and playing around with this algebra, right? And from this construction now, right, I can construct the following objects. I can add these two things up. That will give me a 1. And if I subtract them, I just get back sigma z. And how will you obtain these values? Well, you know what plus plus equals, and you know what minus minus equals. So just add them up, work out the algebra, and you should get 1, and you should get sigma z. And now you're starting to see how we're going to sort of represent this mathematics. Now we have some object, sigma z, made up of the physical measurements we want to construct, right? And where these pluses and minuses are sigma z primes, right? Corresponding to different values. Okay, and I can do the same game with multiplication. And I'd get a 0 if I multiply them, which is expected because this plus and this minus are different, as we did with our a primes, and we discussed how if you have these a prime brackets and these two middle values aren't equal, you'll get a 0, right? Because of the way the measurement system works, right? And it makes sense here, right? Because you need a 0. Okay, what else can we construct? Let's think about this now. I can also claim the following. Sigma z squared will have to equal 1. Sigma x squared will have to equal 1 if I wanted to find measurements along the x direction of spin. And sigma y squared must also equal 1, right? And where does this come from? This comes from what we talked about last lecture. That all of our probabilities, the norm squared, all of the probabilities when you make your measurements must add up to 1, right? So if I square my total measurements, I will get a 1, right? Which makes sense because they must all add up to 1. Unless you're taking superpositions, then you might not get a 1. You might get some weirdness. You might get things adding up and subtracting. Okay, so let's just write down some objects for our algebra. If I have this, I know I get a 0, right? Then by default, if I have this combination, I know I get a 0. However, if I have this combination, I get this out. And similarly, if I have this combination, I get this out. Right, and this just follows from what we did last time with the a primes in our, let's call these bars, because if I say brackets, that's just bracket. Okay, Anson, for that question, do you mind coming tomorrow morning? Because I don't want to review things too much from last time because we have a lot to cover today, but that's a fair question, but okay. This all makes sense, right? I mean, it's just building up from last class, except now we're explicitly defining what we're measuring, right? Instead of the analog to capital A and A prime, like I said, is sigma z and sigma z prime, right? And from there, you can just work out all this algebra. And it's your first example of working out a physical system, right? Some explicit physical measurements. Okay, but now we've constructed sigma z, right? We've constructed an object that equals 1, right? Which I just showed you. But now I want to construct an object for measurements along x and y. And you know, there's a little bit of convention in the way we define these things. But what I can do to construct these objects is I can take the superpositions like I did for sigma z and 1, and I can square them to make sure that those superpositions yield back a 1. Okay, so I'll show you what I mean. So let's say I take the superposition of these two measurements. Okay, so I know that these two measurements will not yield me a 0, right? So now when I square them, if the square of these two measurements equals 1, then I know that this is a good and solid measurement, right? that I can make this measurement physically, right? And we played around with this last week where we had like A prime, B prime, C prime, D prime. And when B prime did not equal C prime, we had a problem. So let's square this. Let's see if we get 1. And then if we get 1, we can construct this as another one of our Pauli operators. Not in the Z direction, because we already did that, but perhaps in the X direction or the Y direction. So let's just work that out. You can work out this square on your paper. Someone can tell me the answer. It always gets a little confusing with the bars, with plus minuses in there. Right, and I'm missing one term, which is this term. So this just equals . So when you work out this square, the algebra is a little messy. You should get that it equals 1 and checks out. And so therefore, this combination of measurements can be a physical representation. And we can relabel this as a measurement of spin explicitly along a different direction. And so we could name it X or Y. These coordinate systems are arbitrary, but in physics, we call this combination sigma X. So I'll write it explicitly in a second.
So I have a question. Why just we can't like add like the first part, like minus plus 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 minus, and then make it like squared?
Sorry?
So why just we can't like add what's inside the brackets? I mean, inside the like square thing, and then just make it squared.
Yeah, you could do that too. I mean, there's a variety of ways to do it. You'll get to the same result. This is just to show that this combination of measurements is physically allowed, right? And you'll see that you have a limited amount of combinations that will yield physical results, right? For example, if I switch the order of these and squared it, I would just get back this object because these two things would be reversed. Right? So it's not going to make a difference in the direction I'm measuring. So all of these sort of combinations are arbitrary as long as you get to the same result. Does that make sense? There's no physical reason why I've done it this way versus the way you just articulated. Is that clear? Okay, so it turns out that the only other combination that will yield me something physical that is unique from this combination that we just squared, that is unique from this combination, because I could just reverse this order and I'll just get back the same thing. So I can't redefine it as a different operator. So it turns out that the only other combination is the difference of these two measurement symbols. So we're going to work that out in a second. I just want to write down sigma x, which is what we just derived. So sigma x equals minus plus, plus, plus minus. Okay. Now what's left is sigma y. So let's work out this square. And someone do this, please, and give me the answer, okay, at the end. Did someone work it out? Give you guys a minute. Feel free to just jump in. It's okay if the algebra is not right. I mean, the biggest thing we all mess up on is algebra, shockingly, but it's true.
Well, I got -1.
Exactly, a -1. And who said that?
Me.
Okay, do you think that's a problem?
Yeah, because it's supposed to square out to get 1.
Exactly, you can't have a negative probability. So right here, just in this simple exercise of just playing around with these combinations, you get a -1. And you should be going, oh my God, what am I gonna do? My whole algebra is ruined. There's no way I can write this all down in some kind of mathematical way. Well, it turns out we have our favorite buddy, I, the square root of -1. And so right here, we see the necessity of complexifying this object because we need to yield a 1, right? And so what we do to sigma y is we complexify it and we get this for sigma y. So very good observation. That's why I wanted you to work that out on your own, just to sort of see how that is an odd thing that you get from working out these combinations and how explicitly you require complex numbers. So therefore, sigma y equals I minus plus minus I plus minus. That's how we define this. So you can work that square out and it will equal 1. Very good, excellent. Okay, let's write out some more identities. This is another one that you might want to use at some point in your... I encourage you to verify these at home. They shouldn't take too long to do if you're so curious. So these are 2 more identities. Just by, we're just building up the machinery and building up this algebra even further. And you're going to prove some of these in the problem set. I mean, they're not in this one, in the following one. Not in this coming one, but in the following one. Okay, and if I take the square of these, I get, think. Yep. Okay, so I just multiplied that out. Right, and it follows from our prior analysis that this is true. So therefore, this identity is also true. And we can start to notice that there's a cyclic pattern. Between our sigma matrices. And these kinds of cyclic patterns are extremely important. They're going to keep coming up time and time again in our construction. So I'll give you a second to write that down. Right, and we can keep building this up. Keep building up the algebra like we did last time, except with these Pauli matrices, you have a lot more you have a lot more, lot of different ways you can play around with them because of the way they're constructed. Okay, so let's do one more identity. And again, I encourage you to verify these and just make sure that they work with how we define them. Okay, good. So let's take the dot product between two vectors of our matrices. Not matrices yet, we're getting there. I have one more thing I can. Right. You work the rest out. I started off this complicated thing, this dot product. And what you'll find is that the following is true. I think that should be a sum, but yeah. Where this is the cross product of two vectors. If you're unfamiliar with a cross product or a dot product, look it up or ask me tomorrow, and I will show you that operation, or even ask Gabe after the lecture. So again, this is just building up, this is just math. I'm not really introducing to you any new physics, but we always need to do this because when we start doing really intricate computations, we're going to need to know this kind of stuff, right? And you always need these tools in your toolkit as a physics student and as a practicing physicist. You need these identities and you just sort of need to work things out quick or whatever, or do an explicit calculation. But I always get satisfaction in verifying all of this stuff I see. That's important. You want to be skeptical. Just because I write it on the board, it might not always be right. I'm not saying I'm going to unpurposely make things wrong, but be skeptical as a science student. Be skeptical, question, verify on your own, question your textbooks. That's very important to do, and it aids the scientific process. And you might find that when you question your textbooks, the writers might be a little smarter than you thought, but at least you learn something along the way. Okay, very good. So now if I have just you know, 3 vectors that are equal to one another, right? Then of course, the dot product squared will be 1. And let's just say these are unit vectors. And remember, all our unit vectors in quantum mechanics are orthonormal. We're in an orthonormal basis where all our unit vectors equal 1. And where all of our unit vectors are orthogonal to one another. Okay, any questions before we continue? Okay, very good. So now we're going to go to the next very important object that you will not be able to live without in this course and in quantum mechanics and in field theory. Okay, we're going to talk about Hermitian conjugation and self-adjoint operators or adjoint operators. And it turns out that, as you can see, the quantum mechanical program is extremely interesting. It's interesting in this aspect. The character of physical law as defined in classical systems is very predictable. It's a very sort of beautiful arrangement. Given initial conditions of any system, you can deterministically tell me exactly how that system will evolve through time. You can't do the same here. We already know that some weirdness happens when the measurement is taken. And so therefore, by default, we have to sort of throw our intuition out the window and try and make sense of all this physics. However, it turns out that mathematics is very, very effective in sort of ignoring all the fuzziness. Why that is the way it is, that's a very interesting question. We can talk about it tomorrow if you're interested. But I always found it fascinating that this mathematical structure, this mathematical program of quantum mechanics works so well. And as we get to dynamical systems, the hydrogen atom, and so on, the harmonic oscillator, you'll see just how scarily efficient and accurate this sort of program is. So what have we covered so far? We've covered the fact that in quantum mechanics, all of our vectors are orthonormal, complex state vectors in a vector space, right? A vector space is just a mathematical object with a bunch of vectors in it. And Gabe is going to go more in depth of the characteristics of a vector space. In particular, in quantum mechanics, we're always operating in Hilbert space. And he'll describe to you all those characteristics. It's a bit more advanced, but it's good for those of you that want to see this through till the end to know these kinds of things. So we're in this sort of complex plane. We're working with these complex objects, and we're doing physics on them. We are extracting measurements out of them. We're sort of playing around with the algebraic properties of such objects. And so Hermitian conjugation is another sort of requirement of quantum mechanics and quantum mechanical systems. And again, it obeys a mathematical principle, as you're about to see, which again is very, very interesting. That these mathematical principles, this mathematical intuition is what's going to help us to understand the physics. So I always want you to just keep that in the back of your mind, that the mathematics is really driving our analysis here. And the mathematics stems from that observation of Stern-Gerlach. So let's describe Hermitian conjugation or adjoints. They're called adjoints in more general terms. Okay, so let's say I have my following measurement. If I take the Hermitian conjugate of this measurement, I put a dagger to denote Hermitian conjugation, I get back this. I get back that they're reversed. So that's what Hermitian conjugation does. It sort of reverses your in and out states, your creation and destruction states. Right? And if we have our unit symbol, if we take the Hermitian conjugate of that, we just get back our unit symbol. And such symbols are defined as self-adjoint. Okay, so now we've defined the operation of Hermitian conjugation. So let's play around with this a little bit. So if I have the following bra, and I take its Hermitian conjugate, what it does is it gives me a ket. Right? Because we're reversing our in and out states. Similarly, if I have a ket, and I take its Hermitian conjugate, I get back a bra. Another property of Hermitian conjugation is if I do this dagger twice, so x dagger dagger, I just get back my original object. Also, can someone mention to me quickly who's looked at Townsend, does Townsend go over Hermitian conjugation in chapter 1?
No, not in chapter 1.
Okay, okay. Okay, so let's work this out more in detail. So if I have this combination, right, which is basically this, except now I have two different measurements, and I take the dagger, then I just get this. That should be a 1. Or I get the following. That's just taking the Hermitian conjugate of two objects back to back. Okay, good. I see people writing, so I will give everyone a second. I'll get used to the pacing a little bit better. I think last time we went too fast, which is not good, but it's okay. That's why we have the YouTube. Okay, excellent. Let's keep building on this more in depth and really see why this is so important. I mean, right now I've just sort of described an operation to you and said, oh, here's this really important mathematics. By the way, which was, I'll just give this as a quick aside. This mathematics was invented by a guy named Charles Hermit, I'm not good with my French, who invented this kind of mathematics over 100 years before quantum mechanics was even founded. And so you kind of see this trend in physics where the mathematics is always sort of ahead of the game. For example, Einstein, and we learned this in our general relativity class, when Einstein needed a mathematical description of curved objects to extend that mathematical description to curved spacetime, he went to his buddy. I forget his name, oh man, I should remember his name. His buddy from college was a math professor in Switzerland, and he went to visit him, and he goes, I need some mathematics for curved spacetime. I'm really struggling with this. I don't know if there's anything here, and so on. And his friend goes, oh man, that's already been done 100 years ago by a guy named Riemann. And so basically, Einstein was shocked. He was like, this is wonderful. All the mathematics I need is right here, done by Riemann 100 years ago. So this is sort of a trend you're going to keep seeing popping up. In field theory, the opposite happens. The physical developments and the physical mathematics were truly developed from scratch by physicists. So this is kind of an interesting historical side. And as I mentioned last time, I think it's really important for any science student to really know the history of science too. And the history of quantum mechanics is really fascinating. Okay. Right, so let's work with something a bit more intricate now. Right, let's take the dagger of this. So I'll give you a second to think about that. Okay, and this should be straightforward. Remember, you could always write this out in terms of bras and kets, or in and out states, or creation and destruction states, whatever you want to call it. That's what we'll do now. So in bracket notation, right, you just get this object, which we've worked with many, many times. So let's take the Hermitian conjugate. You get this. Right? Your in and out states are all messed up and flipped, right? And then you notice something interesting. You notice that this combination is a number, right? And you notice that from last class, these two things are equal to one another by a complex conjugate. So what, in other words, I'll write this down here. When I complex conjugate this object, I get back what I get when I take the Hermitian conjugate. So you see they're related. And so I can rewrite this as the following. I can rewrite this as B prime, C prime star, right, with my in and out states and my measurement symbol, as we've done before, right, where this used to be a kronecker delta, right, with our in and out states at the end. But in fact, we start to notice something, that taking the Hermitian conjugate is very, very similar to just taking the complex conjugate of an inner product. Right? And you know, this just follows from what we've been doing, which is very nice. Like I said, it just sort of spills out of the mathematics. Does this all make sense? Okay, good. Should be straightforward. It's just some manipulations. Okay, and we can really write this more generally in the following way. Let me see, what's the best way to do this? Yeah, that this combination, right? If I take the Hermitian conjugate, I'm starring my inner product, and I'm going to take the Hermitian conjugate of this. And we know that it reverses the order of this object as well. But I'm writing this dagger and this star explicitly separate because they are different. And you're going to see in a second how this dagger is different from the star. But this star will still hold for my inner product, right? The inner product will always just be the complex conjugate when I'm doing the Hermitian conjugate. I'll rephrase that. When I'm taking the Hermitian conjugate of a set of state vectors, if I have an inner product, it's just equal to the complex conjugate. I'll say it a third time. If I have a number and I'm taking the Hermitian conjugate of just a number, that is the same thing as taking the complex conjugate of that number. Okay, hopefully that makes sense. Because it's very easy to get confused when you're first seeing this kind of thing. Okay, very good. And we can write this very generally in the following way.
I have a question really quick.
Yes.
On the third line, at the end, you have like a bracket.
This one?
Yeah, that one, but at the end. You have A prime and then D prime in the brackets.
In this one?
Yeah.
Yeah.
So is it supposed to be A prime, D prime, or D prime and then A prime?
Yeah, sorry. You can put a dagger.
Okay.
Thank you. Okay, good. That is to give you some intuition that daggers and stars are different. I mean, they're very intricately connected, but where the dagger is going to come in, you'll see in a minute, and how it impacts us even one step further is when we move to the matrix description of all of these objects, which we're about to do in a second, which will be sort of the whole foundation for our description of quantum mechanics moving forward. Also note, we haven't even talked about a wave function yet. We haven't talked about anything continuous yet. we're getting there. And on your homework, you're going to start working with continuous objects. So if you have trouble with sort of the kinds of computations you need to do on the homework, just come and see me tomorrow and I'll help you out with it. Just take a look at it tonight. Okay, and in fact, generally, if I have some scalar lambda times some function or state vector x, and I'm taking the Hermitian conjugate, my lambda will be starred, and my other object, my object of state vectors will be Hermitian conjugated, which we'll see what that actually means more detailed in a second. Okay, let's take a 5-minute break and let's come back at 10:30, 10:30 sharp, 4-minute break. And then we're going to talk about why Hermitian conjugation is really, really crucial. Okay? Anyone have any questions in the meantime?
Can I ask the question I had before?
Yes, remind me.
So it was part of the expectation value thing, and I didn't understand one step in it.
Okay, tell me what to write.
So it was like, sorry, I don't know how to like read this, but
That's okay.
so it was like the very first one, right? The big B equals the summation over B prime of like at B prime times B prime times broad B prime.
Got it. So was it this? And I have a B prime here. This?
Oh yeah, before you wrote it as like A prime B prime times B prime times A prime B prime. So that's what I was confused about. Like you put the last one as A prime bar B prime instead of B prime bar A prime.
Okay, no, then that was a mistake. Then you caught it. Yeah. I'll just write it explicitly one more time. This should be this. Yeah?
And
Okay,
then afterwards, the Kronecker deltas would be like Kronecker delta A prime B prime and then Kronecker delta B prime A prime.
Yeah, you just flip the order for the inner products. Okay, good catch. Yeah, when you're not working off notes, you're gonna make random mistakes. So it's good that you caught that. Don't be afraid to. I'm not working off anything typed up and perfectly done. So there's gonna be some little issues. So thank you. Very good. And I knew that going onto YouTube would decrease our attendance, but I'm okay with that. I bit the bullet, but we have you guys here, so that's good. Very good. Let me say hello to some of you. Okay. I see Bob. Hi, Bob. I see Kelly. I know Kelly now. I see Olha. I know Olha as well. I see Jenna. I think I remember you from last time. Are you from California? Good. Okay, I remember. That's very impressive for me. And I see a bunch of black. Okay, I'm gonna start calling people out now. I see Ajay. I see Karina, Kirti, Diego. Oh, good, I get applause. Thank you. I appreciate it. How was everyone's week? Everyone's week was okay? Okay, good. I hope you guys don't feel overwhelmed with the stuff. If you do, feel free to holler. I don't want this to be a stressful experience, so. Okay, great. And Gabe is really nice. So he will definitely explain things very, very thoroughly. He's good at that. That's why he's helping me out. I lack that gift, so. Okay. Okay, so let us get to the big so what. Why is Hermitian conjugation so important? Why are we doing all this, pulling out this dagger? It's because we're getting to a matrix description of quantum mechanics. Okay, that's the idea. We want a matrix description of everything, organized neatly. I mean, we don't want that for any particular reason other than the fact that it helps us describe physical systems. And it turns out that Hermitian conjugation is a requirement for any observable. Okay, the statement goes as follows. All observables are Hermitian. Okay, and I'm gonna show that to you now. So let's look at our unit symbol and see if it's Hermitian, just as a starter. Okay, we see that this object, if I take the dagger, I just get back the same thing. Right? So this is Hermitian. Check. Straightforward. Which is good. If it wasn't Hermitian, then it wouldn't be an identity operator, right? Because you need the same thing in the identity operator. I mean, that's in the definition. You need two A primes or two B primes or two cupcakes or two whatever, two of the same object. Now let's move into our expectation value and let's see if it's Hermitian. One quick semantic note. Note that the expectation value is different from an operator, right? Expectation value is not an operator. They're different things. If I had an operator here, this capital B would become an operator, okay? And it would change the whole construction of this quantity, okay? It wouldn't be this sort of nice thing we're writing out. So don't get confused between operator, physical degree of freedom you want to measure, and the number value of that degree of freedom. That's very, very important. And for those of you that, it's so much easier to use the jargon sometimes because I keep having trouble describing to you what B is. But if I say degree of freedom, it makes total sense. So what's a degree of freedom? For those of you who haven't taken physics, a degree of freedom is just one of the variables in our discussion, or one of the dimensions of our analysis of a physical system. So let's say I'm describing a system in three directions, X, Y, and Z, then that system has 3 degrees of freedom. Let's say I am describing a system of momentum, position, and velocities that also has 3 degrees of freedom. Okay, and those 3 dynamical variables will be geometrically represented. We can solve for them algebraically. We can solve for them taking integrals and derivatives and so on and so forth. And so I'm going to use that language a lot just because it makes things so easy for me to describe to you. So that's sometimes the jargon comes in handy. Although I'm not a big fan of jargon. So in general, I don't like it. I think it's silly, and people use it a lot to try and mask a lot of things. So I try to stay away from it. But if I do say something that you don't get, let me know. It's important. Okay, so we know how we've defined this. Okay, and let's take the Hermitian conjugate. And as you can see, we get back the same result. Okay. And also we should write this condition that B prime equals B star, B prime star, because all observables must be real. You can't have an imaginary observable. And that's also why our expectation value is Hermitian. If this was imaginary, you would change the sign. And so our expectation value would not be Hermitian. Okay, so this is just a reality condition, if you want to use some jargon. Okay, and in the homework, you're going to be working with an operator. So there's this theorist who is trying to construct an operator for this new property of particles called Gleb, okay? And she writes down this operator, and she wants to see if, when she solves the equations, does the operator she constructed yield the right real physical number? And so you're going to work through this calculation. You're going to push through. Then when you get to it, you'll take a deep breath, and you'll see whether she gets the right answer, or you might have to fix her operator. I'm not sure. But you should check if it meets the reality condition. That's important. You wouldn't want an imaginary number. How would you measure that? Okay, does this make sense? And this is why hermiticity is such an important condition in our quantum mechanical framework, because anything observable will be Hermitian. Make sense? Okay. Okay, so let's look at our Pauli matrices. I keep calling them matrices because we're getting there, but we're not there yet. We'll get there in about 5 minutes. So let's look at our Pauli operators. So we have 1 equals plus plus, plus minus minus, right? We have that sigma z equals plus plus minus minus minus. We have that sigma x equals minus plus plus minus, and we have that sigma y equals minus plus minus plus minus. Okay. So this gives us our full set of Pauli operators. You will see in the homework, and I guide you through this, that the language of group theory actually yields all of these objects, and group theory will be extremely important, especially as we get to particle physics, because all of the objects we work with can come from these mathematical objects called groups, and you'll see how this set of objects is actually a representation. A representation is a collection of objects of the group SU2. And in the homework, it tells you why the group name is SU2 and so on. And you might have heard in the pop culture when you see a bunch of physicists talking, they're just like, oh yeah, you know, that's just SU3 cross SU2 cross U1 or something crazy like that. They're just putting together groups to form a larger object, and those groups contain objects of physical significance like this. So it's going to be very important that you work through that example and get some intuition. Okay, so let's test this out. Let's see if sigma x is Hermitian. Right? So work that out. Right, so it changes the order. You take the dagger. Where's sigma x? What you get back is the same thing. No. Changes the order here. See, I made a mistake. Fully take it. Good. Then when you did it. Okay. And you can do the same for sigma y. We can do that now. Oh, I forgot the i's here, guys. My bad. So this is a minus, that's a positive I. Okay. So we've seen that our sigma operators are Hermitian. We've done the same for the unit operator, and sigma z you can work out on your own if you'd like. Okay. People still writing? Yes. Give me another second. word.
The second term in the sigma x plus should be minus plus instead of sigma x.
Yes,
sorry,
yes,
sigma
yes.
x
Yeah,
plus.
yeah, good catch. Yeah.
Okay.
Thanks. Was that Kelly again? Was that you?
Yeah.
Okay, good. So I'm counting on you now to correct the errors. Thank you.
For
Okay,
the,
very good.
for the sigma y, the last part, why is it minus plus for both sides?
Oh, sorry.
Oh, okay.
Sorry. Okay. So we've sort of shown that these abstract operators, not abstract, physical operators, we've constructed are Hermitian, and therefore they're observable. Okay, so now let's move on to matrix representations, and let's sort of start seeing where the matrices are going to come in. And I give you sort of a linear algebra crash course on this problem set. So if you're a little weak on linear algebra, if you've never seen linear algebra, really work through that, learn matrix multiplication, and so it's not hard. It's just like learning new operations, but with different objects. It's really not a big deal. So now we have these objects. I'm just going to call this one like this, right? Where we have some operator or some expectation value or something. Okay? And now this sort of object, and we have a complete set of them, right? By our projection operator. We have a complete set of these state vectors in the complex vector space. A complete and infinite set, right? We could just keep building superpositions. We could just keep adding different measurements. So now this lends itself to a very, very nice generalization, not generalization, but a different description of these objects. So this object collectively is called a matrix element. Okay? And here's how we do this. So this first object, right, or your out state, is always your row number in the matrix. And this last number, your in state, is always the column in the matrix. And I'm going to write this down explicitly. So what do I mean by that? I mean that this in the matrix representation really is equal to this. So this is the rows and the columns, right? For those of you who've never seen this, I'll just write this explicitly. So I have the first row, right? And the first column right here. And here I still have the first row. Now I'm in the nth column. And here I'm in the nth column, and I'm in the first row. And here I'm in the nth row and in the nth column. These are your columns. And so now you're starting to see how we're going to put these things into matrices and build representations and so on from groups. Anyone have any questions on the notation here or why I labeled things the way I did or? Okay, great. So now let's write down our Pauli matrices. Okay. So our Pauli matrices are as follows. And these I want to actually grab. Not really. Okay, and sigma y, you're you're going to derive in the homework. And let's work this through now. I have a plus here and a plus here, minus, minus. So what do I mean by this? This first row and first column element, right, is equal to a plus plus measurement. This number, right, which is the first row, second column, is equal to a plus minus measurement. Right, so let's work this out slowly. I want to make sure you understand what this is doing and why we did this and how it re-gives us the results that we want. And you're going to do this for sigma y. You're going to derive it and see what sigma y is. But you'll be able to get a pretty good guess. Okay, so let's look at this one. So what is sigma x? Sigma x is just minus plus, right? Plus plus minus, right? So do I have a plus plus in here? No. So that's why in the plus plus element of the matrix, I have a 0 for sigma x. Now in the plus minus element, I have a 1. So I can add a plus minus. Right, we're just going to get the backwards, which is fine. Then I have a minus plus element, so I get a 1. Right, and then I have a minus minus, and I get a 0. Right, it just yields from this, which as we said before, we can just work out the backwards thing and get sigma x in reverse. Right, instead of yielding a minus minus, we get a plus plus. And so this matrix actually just gives me all the information about sigma x, and then therefore I can do different operations with this matrix. So when you work out some identities for the Pauli matrices, now I can call them, not this problem set, but problem set 3, you'll be doing a lot of matrix multiplication, right? Because these are just matrix representations of the fundamental measurement objects we've created. Okay, and so now I'm going to define some operations that we can do with these objects. Does that make sense, guys? Okay, good. This is very important because this is where we're transitioning now to a matrix description, or really the description in which we're going to operate in. Okay, so I'm just going to define some operations now, which are important to us. Now that we have a matrix, it's a ket. Okay, we just worked out some operations. Also note that my scalar can always just come right out. And now let's go back to the Hermitian conjugate. Okay, so the order switches. And I'm taking the complex conjugate as well. Ah, Now we can see how Hermitian conjugate's different from complex conjugation. Our rows become columns and our columns become rows. I'm taking, in other words, in linear algebra speak, not only am I taking the complex conjugate of each element, I'm also taking the transpose. So the transpose is when the columns become rows, rows become columns. So the Hermitian conjugate really is the complex conjugate transpose. And since my Pauli matrices are Hermitian, you should play around with that. See if you take the complex conjugate transpose, you get the same result. Right? And another way to think about it, think of a palindrome, mom. If I switch the order, you get the same word back. So the word mom, in this sort of sense, is Hermitian, right? Okay, so now we make the following claim. I'll give you a minute to write that down. Okay, so now we make the following statement, which follows from this sort of analysis. Okay. If this holds, actually, let me think about that for a second. Yes. If B is Hermitian, then this will equal this. Okay, these two objects will be equal, which you can try with your Pauli matrices. Do a quick confirmation. Actually, let's just do that now. Yeah, let's just do that with sigma x. Okay, so I take the complex conjugate. These stay ones, they're not imaginary, so the sign doesn't change. And this, the columns become the rows, right? So this column becomes my first row, and this column becomes my second row. And I get the same result. Therefore, sigma x equals sigma x dagger. Therefore, sigma x is Hermitian. Good. Okay, and I'm going to define one more operation for you today in the last 5 minutes, and then Gabe will take over, and that is the trace. Or in German, spur. I don't know why spur is the same thing as trace, but that's where it comes from. It's actually, it comes from the German word. Okay, so let's do the trace. So the trace is just another operation in linear algebra, which if those of you who are familiar know what it is, but I'm just going to show it because it's important, and I want to make sure everyone is familiar, right? So the trace of, let's say, A prime, A double prime, is equal to the kronecker delta A prime, A double prime. So these two things must be equal. Therefore, I can define my operation of the trace on some arbitrary x as the following. I'd like to say this x has to do with some a prime, and I get the following. Right. So, these two things must be equal because of this Kronecker delta. It's a sum over a prime. So think about this in your matrix. When a prime equals a, that means the row number equals the column number. And in any matrix, those are just the diagonal components, right? So only the so A11, A22, A33, those are my diagonal components. And I'm taking the sum over all A primes. So I'm taking the sum of all the diagonal components. So I'm adding them up. So let's say I have this random matrix called an M, right? I'm just going to make it up. 2, 1, 2, 1, 0, 3, 3, 1, 0, right? The trace of M would just be the sum of these diagonals. So I get a 2. Right? And so this value is A11, first row, first column. This is A22, second row, second column. This is A33, third row, third column. Okay? Some linear algebra 101. And so the last thing I'm going to write down today, I'll give you a second to jot that down. Is that our Pauli matrices are traceless, which means that the trace of any sigma equals 0. Therefore, the Pauli matrices are traceless. So whenever we say, this object is traceless, that means that the trace is 0. The trace vanishes. Okay, excellent. So today we've sort of taken the next leap. Well, we brought in some physical representation. We made these kinds of measurements more explicit, not as abstract. And we've defined some key mathematical properties of our theory. Last class, the key properties of our theory were orthonormality, were complex vectors, complex state vectors, and so on and so forth. Now, our big mathematical concepts were permission conjugation, right? That's the big thing from today. And learning how to take these state vectors and put them into a matrix representation. And so that's very, very crucial. So that's it for today. Thank you guys for coming in. This will be up on YouTube, but trust me, I appreciate those of you that have came in, and now I'm starting to recognize you guys better. So come to these live lectures so I can see you, I can hear you, we can have this discussion back and forth. It's very important. That's why I was hesitant to put up a YouTube channel, but it's okay. Those of you that want to be here will still be here. So does anyone have any last questions, logistics about the problem sets? The problem sets, I'd like them in by 5 today, Eastern. And then the second problem set will be put up today as well. And same due date next Saturday, 5 Eastern. Just so I have time to look at them over the weekend and return them to you Monday. I won't return them to everyone, but if something looks a little crazy in a good way or a bad way, it's okay. I just want to make you guys aware of that. Okay, any last minute questions before I turn it over to you?
I have a question quickly about submissions. So how,
by the way, your name?
Oh, my name is Sanat.
Danat, okay.
Sanat.
Vanat, okay.
No, Sanat. Anyways,
Spell it. Sorry, I can't hear you.
It's fine. S-A-N-A-T.
Okay, Sanat, sorry.
Yeah, no problem. So in what format do you want the problem sets to be submitted to you?
Yeah, you can do them on paper and scan them. You can do them in LaTeX, if you know
Okay.
LaTeX. It's up to you.
Thank you.
And I encourage you to be as descriptive as possible. I like a lot of writing, and I like a lot of thinking. You might not get because, you know, if the goal is to do research, right, then you ought to really tell me your process, right? I think that's kind of important. Anyone can do a computation, but the thinking behind it, the understanding of the physics is what's more important to me than getting the right answer, right? So you might get the signs wrong, you might get a factor of 1/2 wrong, but if your logic was right, that's going to stand out way more, and it's going to mean more. It's going to help me identify who's getting the physics and who's just able to memorize some computation. That's trivial, in my opinion. I've always felt that people can learn how to compute. Humans are very intelligent and have the computing gift. I think all humans instinctively compute and recognize patterns. So that's not so exceptional, although you need to know how to compute. But what's even more important to me is that you know the physics, because that takes more time and that takes more of a deeper understanding. Okay? Okay, anything else before I turn it over to Gabe? Any questions about it? But a scan is fine, or LaTeX if you so desire, if you feel comfortable with it, but it's not so important. I don't want you to waste time LaTeXing if it takes you 2 hours to LaTeX a few lines. Don't do it. Okay, great. Okay, Gabe, are you there?
Yes, I am.
Okay, hi, Gabe. Okay, I'm going to make you the host, and I'll leave, and maybe I'll jump into the problem-solving session a little bit into it, just so I can get some tidbits from you as well. But,
Sounds good.
all right, thank you, everyone. We'll see you next week. Thanks again.